Okay, grade 9. So here we are in the second half of outcome number 1, and we're looking at properties, chemical or physical. Chemists classify properties to gain a better knowledge of matter. So a physical property is a property you could figure out without making anything new. So, like checking out density, measuring the boiling point, melting point, seeing how soluble something is, looking at what color it is. Does it have, crystal structure? Is it lustrous, which means is it shiny? What state is it in? Solid, liquid, or gas? Has odor or taste? You could figure all this out without changing the chemical. A chemical property, though, describes how a chemical reacts with something else. So, for example, if something burns or some silvery chemical turns white, or if there's an explosion, or if something rots, or if something is poisonous. Basically, what a chemical can react with and how it reacts is its chemical property. So, for example, gasoline, physical property, it is that it has a boiling point of around 60 degrees. It's not soluble in water, has a slight yellowish kind of tinge to it. It's a liquid at room temperature. It has a horrible taste, and it definitely has a smell that you can notice. Okay, but a chemical property of gasoline would be that it's poisonous and that it burns. Try another one. Physical property of water. Density is 1, boiling point is 100, melting point is 0. Lots of things are soluble in water. It doesn't really have a color or crystal structure. It's not really shiny. It's a liquid at room temperature. It doesn't really have an odor or a taste. Chemical property of water would be that if you put electricity into it, it breaks into hydrogen and oxygen. Okay, and water will react with some chemicals. Water reacts with potassium and creates its own sort of chemical reaction there. Properties can be classified as quantitative or qualitative. Anytime it's a quantitative property, it's something you can describe with numbers. And if it's a qualitative property, it's something that you could describe. So, for example, density, you could put a number to it, right? Age, you could put a number to it. Those are quantitative. Brown, you can't really put a number to that. So that's a qualitative property. Something that is smooth, you can't really put a number to that either. Different kinds of elements. So on the periodic table, everything to the left side of the staircase is a metal. It conducts electricity, heat. It's malleable, which means you can shape it. It's ductile, which means you can stretch it out into a wire. And on your periodic table, there's a staircase, and it's on the left side of it. The nonmetals are on the right side of the staircase. They don't conduct electricity. They're brittle. They're dull in appearance. They're usually solid or a gas. And so like sulfur, fluorine, carbon, oxygen, those are all non-metals. Metals up here would be like iron and aluminum and copper, and they're on the left of the staircase. Lining the staircase are metalloids. They kind of behave like metals or non-metals, and we'll look at that when I pull up a periodic table. Okay, and then continuing on, properties of matters can change, so we're going to be looking at that. So there's two kinds of changes you're responsible for. There's physical changes, where a substance changes form from one to another, but there's no new chemicals being made. Okay, so like if you start with an ice block and melt it to water, it's still just H2O. And if you take water and heat it up till steam, it's still just H2O. And if you put salt in water, it's still just salt and water. You can easily separate them out, right? So physical changes are no new chemicals are made is the most important thing, but they also tend to be reversible. Okay, and then chemical changes where one or more new chemicals are made. So in a chemical change, the chemicals change, and this is usually irreversible. So some chemical changes, burning gasoline, cooking eggs, photosynthesis, cellular respiration, those are chemical changes. Now, I'm not sure why I'm saying next year move this back 2 pages, but it's there nevertheless. I think this might be the start of topic 2, but we'll see. There's several clues that indicate chemical changes happened. It has to be 2 of these clues for it to count. There's a heat change, starting material gets used up, change in color, if gas bubbles form, if 2 liquids form a solid or a precipitate forms and 2 liquids are mixed, if the change is difficult to reverse, or if a new chemical with new property forms. This is all clues to indicate that a chemical change has happened. And so we have some practice here. Let's see. A spoon is dipped in egg and turns black. That's definitely chemical change. You have a change in color. difficult to reverse. New chemical, new property forms as well. Cutting grass, that's a physical change. Why? Because while it's not really reversible, you haven't made anything new. Cutting grass is just smaller pieces of grass. However, if you let the grass sit and rot, it produces heat, it changes color, it's difficult to put it back. New chemicals, new properties form. Starting material gets used up. That would be a chemical change. Two clear liquids form a yellow solid when mixed. That is a chemical change. You've got the starting material getting used up. There's a change in color. It's difficult to reverse. A precipitate forms when two liquids are mixed, and of course, new chemical, new property forms. Melting sodium chloride sounds like a chemical change, but it's just melting. In melting, you're not making any new chemicals, and you can reverse it. If you let it cool down, it will come back to the way it was before. Then we did a lab in class, and so yeah, this is all part of outcome 2. Law of conservation of mass. Mass before reaction, mass after reaction stays the same. And so if you start with 32 grams in a chemical reaction, you finish with 32 grams. The law of definite composition says the formula for compounds are the same everywhere in the universe. So the formula for water here on Earth is H2O. And water on the moon, which by the way they just found on the bright side of the moon, is also H2O. And water on Tatooine would also be H2O. Sorry, a little bit of Star Wars in there. Okay, and they have because they're pure substances with constant composition, it's the same everywhere. So Mr. Spock, if he wanted a glass of water on Vulcan, it would still be H2O. And by the 19th century, they actually found a way to break elements into their compounds by using electricity. This is the process called electrolysis. All you have to do is put electricity into a compound like water, and it'll break it up into its elements, hydrogen and oxygen in this case. You'd want to use a little bit of baking powder, and you would never plug this into the outlet because that would be dangerous, but you could actually use a 9-volt battery, strip the wires off of it, and put a little bit of baking soda in with the water, and you could actually get hydrogen and oxygen forming. Don't do like me, because I used a different chemical and I actually accidentally made chlorine gas, and I told you the story of how I gassed myself that one time. In any case, they used this after electricity was invented to discover a whole group of elements, potassium, sodium, magnesium, and many other ones, just by putting electricity into compounds. And then we did lab mass and chemical change. And then we're going to look at breaking bonds. So what holds together chemicals are bonds. Okay. And so in order to break a bond, you have to put energy in. That means the opposite. In order to make a bond, energy is released. And all chemical reactions involve some sort of energy change. Whether you can measured or not is a different story, but they all have some. And an exothermic reaction is one where the energy is released as heat. So burning gasoline, exothermic reaction. The reaction side of a hot pack, you know, those ones that you have for your sports team, or if you have a bag of chemicals, you punch it, it breaks the seal between two chemicals inside the bag. All of a sudden it gets hot. That's exothermic. Think of exo as exiting. The energy is coming out of the reaction and going into the surroundings. Okay. Oh, I should probably tell you this part too. Reactant arrow products. Okay, so the stuff that goes into reaction is called the reactants. I mean, that makes sense. The arrow is the A, and then the things that's produced is called the products. Okay, so that's always reactants, arrow, product. So in this case, what are the reactants? Well, there they are over there. CH4 and the 2O2 are reactants. What are my products? Well, it'll be on the right side of the arrow. So carbon dioxide, water, and the energy are my products. In an endothermic reaction, reaction absorbs energy. So like cooking food is endothermic, right? You have to put energy in, and it takes the energy and changes the bonds and cooks your food, right? You cannot uncook an egg once it's cooked, and the products are different. So what are some examples of this? So endothermic reaction, energy has to go in to make it work, like cooking food or photosynthesis or vitamin D production where the sunlight shines on you to make it. This one, the exothermic would be like cellular respiration would be exothermic as well. These are all endothermic. Look at here in this reaction, endothermic, so the energy is going into this. So this is the electrolysis of water. There's the energy going in. Here you're burning methane gas, and so there's the burning part, and then you see there's the energy coming out of it. Okay, and then what's in the bag is the lab that we did in class as well. So some test your knowledge questions. So what are the reactants? So remember, reactant are all products. So here's my reactants: carbon dioxide, water, and sunlight. My products, because there's my arrow, right? RAP, R-A-P. And so there's my products, the two of them. There they are. Is this endothermic or exothermic? Well, it looks like the energy is going into the reaction. So endo, it's going in. What's the special name for this reaction? You recognize carbon dioxide, water, and sunlight making sugar and oxygen. That's good old photosynthesis. And then here's some classify as exo or endo. Chance for you to do some practice. Burning gasoline, heat comes off, it's exo. Cooking an egg, you have to put energy in to cook it, that's endo. Splitting water into hydrogen and oxygen, you'd have to remember that we have to put either an extreme amount of temperature heat into that or electricity, so that's endothermic. The reaction in a hot pack, so you punch the hot pack, it gets hot, the heat's coming to the surroundings, so that's exothermic. For these ones, I would do this one first. Breaking a bond, I know that you have to put energy in to do that, that's endo. Forming a bond is the opposite, so that's exo. And then cellular respiration, that's, you eat food and then you give off carbon dioxide, water, and energy for life. That's definitely an exothermic reaction. And there's some information about the making of dynamite. And then we can look at reactivity. Okay, and so this chart, so here's how it works. For the metal to become more reactive, it has to move this way and then down. So this corner here is the most reactive metal. Francium is the most reactive metal in the universe. Okay, so if you're looking at these four here, right, in this spot, this one would be the most reactive. If you're looking at these four in a row, cobalt would be the most reactive, it's closer there. If you're looking straight down this way, these four, strontium would be the most reactive out of those four. So always moving down and this way becomes the most reactive metal. And there's a worksheet for this that I'll have posted on Google Classroom as well. Non-metals, opposite. As you go this way and you go up, they become more reactive. So if I was looking at not this row, so you got to remember the very last row is called the noble gases. They don't react with anything. But if I looked at these four for reactivity, the one highest up and to the right would be the most reactive. So this would be the most reactive. If I was looking at these four, the most reactive one would be chlorine. If I was looking overall at the most reactive non-metal in the universe, it's going to be fluorine. It's not this one, obviously, helium, right? Even though it's a top right, you don't count any of these. If helium was the most reactive non-metal, it'd be crazy. Someone would give you a helium balloon, you'd take a breath of it in, and it would instantly kill you. No, this is the most reactive one. Okay, and so most reactive metal in the chart, francium. Most reactive non-metal, fluorine. What's more active out of those four? It will be the one that's closest to the bottom left. So sodium, potassium, magnesium, calcium. Sodium, these four, so that means potassium is most reactive. Which one is the least reactive metal out of those four? It would be the magnesium. Which one is least reactive out of these ones? F, O, S, and Cl. They're all up here in a F, O, S, and Cl. The most unreactive one would be sulfur. Which one's the most reactive out of those four? Again, that would be chlorine. And then name an element that doesn't react at all. Any one of these would work for something that doesn't react at all. That's for another lab we're going to do. And that's as far as we'll get for these set of notes. We'll stop there.